It's now my pleasure to introduce again Professor Christine Doan to give the George Darwin lecture, Black Holes, Einstein's Gravity and Rocket Science. This should be exciting.
Okay, thank you very much. So, black holes, Einstein's gravity, yep, you can see what those two have to do with each other. But why rocket science? Well, hopefully by the end of this talk, I'll have told you why rocket science folds into the title as well. But firstly, I'd just like to say thank you for the Darwin Lectureship Award. It's for an distinguished and eloquent speaker, so no pressure then. And, but I was especially very happy to receive that award, as many years ago now, more years than I care to count, I was a graduate student in Darwin College in Cambridge. And its claim to fame, apart from that it is the Darwin family house, is that it's the only college with its own island. And very beautiful it is too. So thank you for the honour of the lectureship, and I'm just very happy to see a connection across more years than I like to count of my academic life. So let's go on to think about black holes. And there's a wonderful quote from Red Dwarf, for those of you who are old enough to remember that old sci-fi program. The thing about a black hole, its main distinguishing feature is it's black. And the thing about space, your basic space color is it's black. So how are you meant to see them? Looking for a black hole on the black background of space, that's going to be very, very difficult. And another thing I want to fold in is that we are 2 days away from the centenary of Einstein's gravity, where Eddington gave an announcement to the Royal Society on November the 6th in 1919, announcing that the data he'd taken from a solar eclipse supported Einstein's new theory of gravity and not Newton's. And black holes come out of Einstein's theory of gravity, and so I'd just like to highlight that as one of these nice coincidences, that we're 2 days away from that incredible announcement that Einstein's gravity was the one supported by the data. So what I'm going to do in this talk is I'm going to talk about Einstein's gravity. Black holes come out of Einstein's gravity. They're the ultimate extrapolation of Einstein's ideas for how gravity should behave. And then I'm going to explain how rocket science actually reveals these black holes and allows us to explore Einstein's gravity in the strongest field regime. So that's where we're going. And let's just start then by running through Einstein's gravity, running through the big idea of Einstein's gravity, which is that gravity is warped space-time. That you think of space and time like the surface of a trampoline. I do actually have a trampoline. I got my department to buy me one. My head of department looked at me like he couldn't quite believe what I had just asked. And he said yes, just to stop this conversation, which seemed to him to have gone very surreal. But it's the best way to explain Einstein's big idea about what gravity is. You have the surface of space and time like a trampoline, and it's stretched out with no mass on it, it's flat. You put mass on the surface of that trampoline, and it curves the surface of the trampoline, not just where the mass is, but it curves the surface further out away from that. And then anything that travels over the surface of space-time follows the curvature of space-time under its own feet. And so even if it's going in what would have been a straight path if there had been nothing bending space-time, then that path is curved because the surface over which it's traveling is curved. And so the nice way to draw this is to put ants on some curved surfaces, to put ink on their feet, paws, I'm not a biologist. They're very obedient ants, so you set them off and you say, go north, go straight north. And on a flat piece of paper, the ants go directly north, and if you set them off parallel, they stay parallel. And everything is fine. But if we put them on a curved surface, if we put them, say, on the equator of a sphere and say go north, they go north in a standard straight line path, a natural way for ants to walk, left foot, right foot, middle foot, left foot, right foot, middle foot. I don't think that's how ants walk either, but I'm not a biologist. And as they get closer and closer towards the pole, clearly they get closer to each other, and they could think there is some strange action at a distance force that is dragging them together. We can call it a force field. Yes, we could also call it that you're walking in a straight line on a surface that is curved. And so this was Einstein's big idea, that there is no action at a distance force. The moon's here, the Earth's here. Look, no hands, we'll call it a gravitational field. No, the Earth is here, and its mass warps the surface of space-time. And then the moon is here, trying to walk in a straight line path, but the surface over which it is traveling is curved, so its path is curved. And that's it. That's the big idea in Einstein's gravity. And it's just very different to the Newtonian conception of gravity, which was just a fantastic leap of imagination. The moon is here, the Earth is here. Maybe that's the same force keeping the moon in orbit around that makes an apple. It was an incredible leap of imagination. But in terms of that bigger question, in terms of the what is gravity, Newton was famously silent. In fact, he said, and I think in Latin, because it sounds better in Latin, I frame no hypothesis, which translated into plain English means no idea, I think I've done enough, actually, my equations are great. So Einstein's idea of gravity gave us a way to think about gravity, gave us a way to picture gravity, not just a set of equations to describe the effects of gravity more accurately, although he did that. He gave us a way to think about gravity, to draw gravity, although we normally draw it in 2 dimensions like this, but obviously you're warping space in 3 dimensions, so maybe you really need to draw it like this, which gets very difficult. And actually you're warping time as well, which I really can't draw, so we'll do it in 2 dimensions from now on. So that's the big idea. And this is what Eddington's expedition was all set out to test. Does Einstein's idea work that the space and time is curved by mass, so that anything that's going across the surface of space and time, its path is curved because the surface is curved? And the idea that they had to test this against Newton's predictions is that, well, okay, you can have the most curvature in our solar system is round the limb of the sun. And so if there happens to be a star that's projected close to the limb of the sun, then its starlight has to go round these very curved regions of space and time. We think light travels in straight lines, and so we'll see its apparent position shifted away from the sun. But obviously the sun is very bright, and this is why he had to do it in an eclipse, in order to blank out the very bright light from the sun and see the much fainter light from the stars behind and measure their positions. And so this is what the whole trip, they had to go to some Pacific island. Astronomy always seems to somehow involve going to really interesting places, though I think his Pacific island might have been a little more life-threatening. But once he was there, they did their eclipse work. So the position of the sun is here, what they were expecting to see. Here are the starlight. Here would be the stars that they could see. And then they'd expect that these nearby stars, the ones projected closest to the limb of the sun, they're the ones that go through the most highly curved bits of space and time. And so they're the ones whose apparent position gets shifted the most. And if you compare that with the sun eclipsed to where the star positions are when the eclipse isn't happening, then you see this shift in the positions. And this is what Eddington was trying to measure, and this is what he was announcing the results of at this meeting in the Royal Society 100 years ago and 2 days to the day. So Einstein's gravity works. Einstein's gravity predicted correctly where the star position shifted, Newton's didn't. And so this was some real strong evidence that Einstein's idea of gravity, Einstein's warping of space and time, is really what's going on when we're looking at gravity. But just so you can see some of the original data, here's one of the original. This is how hard it is. You can see the positions of the stars highlighted there, just about. Here's a sketch map showing how it's really very difficult to do. But nonetheless, they were able to do this. They were able to see that shift in the stellar positions, and that shift matched what Einstein's gravity predicted and not what Newton's gravity predicted. So then this is the way to think about gravity. And so you take Newton's equations and you throw them away and you put Einstein's curved space and time there instead. And so this gives you the kind of picture of our solar system, obviously not to scale. Here's the sun, and it's warping space and time. And here's the Earth in this little green dot, circling around, orbiting around, because of the curvature of the sun underneath the Earth's orbit. So it's following a straight line path on a surface that's curved. So what would happen if we made gravity stronger? Well, in Einstein's equations, if you make gravity stronger, you make space and time more curved. So let's squash the sun into a smaller and smaller space, and then we can start to think about some of these more and more highly curved regions of space and time. And what we've done, by squashing all the mass of the sun into a smaller space, is we've now revealed these regions. We can get closer to all that mass, so we can get into more highly curved regions of space and time. We've got a stronger gravity. And if we've got stronger gravity, we've got a faster velocity that we need in order to escape from the surface and go to infinity. So let's do that again. Make the sun squash all its mass even smaller into an even smaller space. We can get into these regions of even stronger gravity, even more highly curved space and time. So the escape speed from this surface is now going to be very much higher. And then we can do it again. Only now, if we take these equations to their limit, then we reach a point where the velocity to escape is equal to the speed of light. This is called the event horizon because nothing can go faster than the speed of light, so nothing from within this can ever get out. And then you can take Einstein's equations even further. You can say, well, what's down at the bottom? And Einstein's equations will go there, and they say, well, what's at the bottom is an infinitesimal point of infinite density, a singularity. But by which time you might be starting to get quite twitchy. Okay, we had tested Einstein's gravity in our solar system, in these quite weak gravitational fields. And we've now extrapolated it. We've made gravity stronger and stronger and stronger and stronger until we got to a point at which light could not escape. And then we crush everything out of existence in a singularity. An infinitesimal point of infinite density. Normally in physics, when you get infinities out, that means you have taken your equations somewhere they didn't really want to go. And so there's always this kind of question, well, okay, that was very interesting extrapolation. We've tested these theories up on solar system strength gravity. Yeah, let's try and test them down here, shall we? Let's see how much of this extrapolation actually we can find evidence for in the physical universe. But then, of course, we're back to where we started. We're looking for a black hole on the black background of space. And so how do we test this? Well, as I'm sure all of you are aware, and in fact most of the planet is aware, it's been estimated that this iconic image here of the shadow of the black hole event horizon in M87 has been seen by something upwards of 4 billion people. By the time you count the number of front pages in every newspaper in the world that it ended up on the front page of, they reckon something like 4 billion people saw this image. So I think I'm justified in calling this iconic. And to put it in context, here's a view of the sky containing this galaxy. So here's 100,000 million stars like the sun, some a bit bigger, some a bit smaller. And the whole size of this image is something like the size of the full moon in the sky. And then we zoom in, and you can see actually there's some sort of activity from the center. There's some sort of jet that's coming out. And then this iconic image down here is this shadow of the event horizon of the black hole. And to give you a picture of the size of this, if this is like the size of the moon in the sky, this is like being able to read a newspaper in New York from a sidewalk cafe in Paris. That's how small it is. That's how small the angle is that they were able to resolve with the Whole Earth Event Horizon Telescope. So what we're going to do is we're going to talk about this image in a little more detail. I'm going to show you actually what it is that they're seeing. But for now, what I want to highlight is that actually we're not looking at a black hole on the black background of space. Actually, we're seeing a shadow. And the only way we're seeing a shadow is because there's something around the black hole that's emitting light, well, emitting radio waves. And that light is what we're seeing the shadow against. Without that light, there wouldn't be a shadow to see. And this is actually from material that's falling towards the black hole. The enormous amount of energy as it's falling down in this very strong gravitational potential, some very small fraction of that energy is being liberated as energetic particles, which are then emitting these radio waves and submillimeter, and they're producing this halo of light, which we're then able to see the shadow of the black hole against. But this is incredibly dim. This is an incredibly dim, fuzzy little bit of light. Not only is the size scale of this image really hard to see, but it's incredibly dim as well. This was a truly heroic observation. So if we don't want to be heroes, if we want to do something that's a bit easier, why don't we study black holes where the material falling onto the black hole is much more, where there's much more material, where there's much more energy emitted, where they're actually bright and easy to see. And so this is what I've done for a living for the past 30 years. What I've done is go and look at bright objects, the sorts of objects where we have a black hole, but it's not a black hole on its own on the black background of space. It's a black hole with material in a binary system. There's a companion star, so there's a source of material that can fall down towards the black hole. And the enormous amount of gravitational energy that gets liberated from this enormous gravitational field, it can be intensely bright. And so you can have this material getting heated up by the gravitational energy and glowing, not just white hot or even not just red hot or white hot, but X-ray hot. And so you have this X-ray intense emission from the material, kind of like its last scream before it slides underneath the event horizon and disappears from the universe forever. So if we could look at the sky with X-ray eyes, we could see nothing because our atmosphere gets in the way. Our atmosphere is mercifully completely opaque to X-rays. And so from the ground, we can't use ground-based telescopes to look for high-energy radiation. The atmosphere starts getting opaque in the UV, and in the X-rays, it's just completely black. So that means we need to get above the atmosphere, and that means we get to play with rockets. I'm a rocket scientist. That's always a good way to introduce yourself at parties. So the very first sounding rocket flights that would get above the atmosphere, pretty soon they decided, oh, let's put an X-ray detector on one of these. They were expecting, well, I don't really know what they were expecting. They thought maybe solar X-rays would get scattered from the moon and maybe they could see them. But they were just, let's put an X-ray detector on a rocket because we can. And this was the early 60s, the very first years of the space race. And they did not discover X-rays from the moon. What they discovered were intensely bright X-ray sources that were these black holes and their slightly less extreme cousins, the neutron stars, with their X-ray hot, glowing accretion disks highlighting their position, just making them incredibly easy to see. And we now have, of course, much better X-ray instruments than those very first, very crude, almost like a Geiger counter on a rocket. And this was one I was involved in. One of my first postdoctoral positions, I worked for NASA. I was a theoretician. I was working on the structure of the accretion flow, trying to understand how it produced all that intense X-ray emission. But I was working at NASA at Goddard Space Flight Center, where the group were involved with building an X-ray telescope that sat in the payload bay of the space shuttle. So I got the opportunity to be part of the team that was in ground control, wearing the snazzy headset, controlling an X-ray telescope in the payload bay of the space shuttle. It was amazing. It was just an amazing opportunity, especially when you're a theoretician. But I didn't press any buttons. And so it's really amazingly exciting to play with rockets. Obviously, it's quite a high-risk business. You take your incredibly sensitive, incredibly delicate instruments, and you put them on top of a lot of high explosive. You light the blue touch paper, and you stand very well back. But the sorts of data you can get from these instruments and what they reveal about strong gravity is really worth the risk, as I hope to describe in the next couple of minutes. So what might we expect to see from that accretion flow? We've got material spiraling in towards the black hole. It's falling under gravity. As things fall under gravity, you get energy out. And you've got this material, gas spiraling around, and the orbits are such that inner orbits are going around faster than the outer orbits, and the gas streams are rubbing against each other. There's some sort of friction that's heating this gas up and allowing it to slide inwards and get even closer to the black hole. And so if you think about this in the simplest possible way, you'll think, okay, well, if there's some sort of friction, that'll heat the material up. When you heat material up, it glows hot. If you've got enough material, it's like black body radiation, like an electric element on a fire. And we know quite a lot about this, so you can make some very, very simple back-of-the-envelope models. You can say, okay, out at large radii, there's not very much gravitational potential energy. And we've got a very large area to dissipate all that area over. So we'd expect that the temperature that we get from that annulus would be quite low. But as the material slides further in, as you go closer in, there's more gravity. But there's less area to dissipate that more energy over. So the temperature goes up. And then we'll do it again. So the material's sliding in towards the black hole. Every time you slide in further, there's more gravitational energy, there's less area, so you get more temperature. And so you can do that all the way down to where? How close can you get to the event horizon? Well, what does Einstein's gravity say? Well, first of all, before I tell you what Einstein's gravity says, I'm going to tell you what Newton's gravity says so we can compare. In Newton's gravity, if you have radius across here and we plot the energy of a particle, then we can clearly see if we've got something orbiting, there's kind of two bits of that energy. There's Newtonian gravity, which goes as 1 upon r, so it's attractive, wants to go further in. But there's also an angular momentum barrier. If you're going around and you move further in, because angular momentum's conserved, we've all seen this on the ice skaters, if they start themselves spinning with their arms out, they pull their arms in, they spin around much, much faster. And then anything that's not particularly well held down, like the hair, will kind of spin, will go outwards. And so there's some sort of outwards that will push you back. And this is the angular momentum barrier. And so if you add those together, that's what Newtonian orbits look like. There's a minimum in the energy, which is occurring at a single radius, and that's a circular orbit. Circular orbits are minimum energy orbits. So we can always have a bit more energy, in which case we'll go between a minimum radius and a maximum radius. That's an elliptical orbit. Or if we've got much more energy, we can come in from infinity to a smallest radius, go back out again. That's a kind of like a comet coming in and doing a hyperbolic orbit. And those are the sorts of orbits you get in Newtonian gravity. But Einstein's gravity is slightly different. Remember, it gave different results for the bending of light rays around the sun. And so in Einstein's gravity, there's effectively an extra term that you get. It's going as 1 upon r cubed. You've got everything that you had before. You've got your standard gravitational potential. You've got your standard angular momentum barrier, but there's this effective extra term. But because it goes as 1 upon r cubed, you only actually notice it at very small radii, at very strong gravity. But you can see it just changes the shape of this total energy. We've still got circular orbits here, and we've still got elliptical orbits if we've got a bit more energy. These are all stable orbits. Anything that's got a minimum in an energy equation, that's a stable orbit. If I drift outwards, gravity will pull me back in. If I drift inwards, the angular momentum barrier will push me back out. So anything where you're in a minimum is nice and stable. Yeah. But that minimum only exists if gravity isn't too strong. What happens as you try and do circular orbits closer and closer to the black hole? You start off with an energy that looks like this, then like this, then like that. Now that's a problem, because here we were saying if I go inwards, the angular momentum barrier pushes me out. If I go outwards, gravity pulls me in. We've got a minimum, so it's stable. But here, there's no crash barrier on the inside. I don't have anything pushing me back out. If I just slide inwards a little bit, I'll keep on going inwards and I'll spiral into the black hole. This is not what you got in Newtonian gravity. It's very different. It's not the point at which I'm going around the black hole at the speed of light. Because you could think, well, maybe in Newtonian gravity, because it didn't have the light speed in there, obviously if I was going around in an orbit at the speed of light, there'd be trouble. This is not where you're going round in orbit at the speed of light. It's quite close to the black hole. It's 3 times bigger than the size of the event horizon, but it's not the event horizon itself. That's 3 times smaller. And it's not this place where you'd be going around at the speed of light. That's 2 times smaller. It's just a place where the angular momentum barrier is no longer strong enough to compensate for gravity being stronger than in Newtonian ideas. You can still orbit in a circle here. If you have a fly-by-wire computer, then correcting your path every time you drifted slightly inwards to the black hole, you could orbit around in a circle. You could still escape. That is not the problem. The problem is most particles in an accretion disk do not have a fly-by-wire computer attached to them. And so when they get to this point, any small perturbation, and they quickly spiral into the black hole. And so that tells us this accretion disk around a black hole, according to Einstein, it gets hotter and hotter and hotter and brighter and brighter and brighter until it gets to this last stable circular orbit, at which point it slides quickly towards the event horizon and is lost to the universe forever. Okay, that's testable, because you can work out the temperature of this brightest, hottest bit of the disk that's close to the event horizon, that's at this last stable circular orbit, and you can work out the temperature that you'd expect to have for one of these 10 solar mass black holes formed from supernova collapse of a massive star. And it comes out at about 10 million Kelvin, or 1 kiloelectron volt, depending on how you want to call it. It's X-ray hot. Okay. There were some interesting things that we have to fold into this. So remember, here I've done a sketch that had my disk as you'd see it if light travelled in straight lines. But if there's a black hole here, light does not travel in straight lines as seen by us, because space and time are strongly warped around by the black hole. And so what you have to do is you have to correct for the fact that your disk isn't quite so clean and flat as this, but you have to correct for the fact that you can see rather more of the far side of the disk. This is the far side of the disk bent upwards because of the black hole lensing the light. I'm just going to show you that in a bit more detail. You've got the black hole here. We're over here, so we see this side of the disk as per normal, but the far side of the disk, the light gets bent around, and so we see rather more than you'd be expecting if light travelled in straight lines on a flat space-time. And you could get really funky, and you could see the underside of the disk as well if this disk doesn't completely block all of the equatorial plane. Whoops, wrong way. And in fact, you can also see on this image, you can see there's a little ring of light in here. And that's the point I was talking about. Here's our last stable circular orbit. These are some amazing simulations done by Jeremy Schnittman. Here's our last stable circular orbit. But inside that, you see this ring of light. That's the point where light itself is orbiting around and getting caught in that little circular bit there. And in fact, that's what we're seeing in this iconic image of M87. This bright ring here, it's photons that are orbiting around the black hole. The accretion flow in this black hole is so dim, so pathetic, so diffuse. Actually, we're really hard pushed to see the accretion flow and the last stable circular orbit. What we're seeing in this really, really wimpy accretion flow is we're seeing the photons that have been caught for a while and are circling, orbiting around the black hole. Because when you're looking at really, really wimpy accretion flows, you don't get much light out. So let's go and look at the really bright accretion flows, the ones where we can start to see, okay, is there really this last stable circular orbit? How could we find out? Well, we could go and look with an X-ray telescope above the Earth's atmosphere, and we could even start to try and see whether our black holes are spinning. If the black hole is spinning, then it drags space and time around with it, and this last stable circular orbit that's going to be the edge, the inner edge of my accretion disk, that's going to get dragged inwards and give us a region of even higher gravity, even more luminosity, even less area, so even higher temperature. And so a non-spinning and a spinning black hole, there should be some noticeable, observable differences. So let's go look. Here's some real data on a real black hole. And what you've got here in red is data from one X-ray satellite. In green is some data from another one stitched together. And this is a spectrum, and it's very like those back of the envelope little cartoon ideas I just sketched for you. A sum of thermal black body components up till some peak temperature, and then, then there's a small tail to higher energies, but that's quite a small tail. The majority of the power is in this thermal component that looks really like the sorts of components that we just sketched a few slides ago. So can we find out what this inner edge is? Can we find out whether the black hole is spinning? Can we test Einstein's? Yeah, kind of. We've got some problems. What we see is the flux. To translate that into a luminosity, we need to know the distance. And we need to know the distance quite accurately. And these are black holes across half the galaxy, and we often don't know these things very accurately. We need to know the inclination of that disk as well, and that's something we often don't know particularly accurately either. So if all we have is just one spectrum, well, but we don't just have one spectrum. We have a whole series of spectra, because these are sources where the mass accretion rate from the companion star through the accretion disk, it varies on timescales of days and weeks and months and years. If you have an X-ray light curve over a timescale of a couple of years, you can see the X-ray emission from this X-ray hot disk changes dramatically by orders of magnitude. And this happens in basically all of these systems that we're looking at. And so on these very nice observable timescales, days, weeks, months, the mass accretion rate through the inner part of the accretion disk going onto the black hole is changing. And that gives us a different way to look at that last stable circular orbit idea of Einstein's gravity. Because even if we don't know the absolute luminosity, because we don't precisely know distance, we know it hasn't changed. And so what we can do is we can look at the mass accretion rate through the disk on one day, and then when that mass accretion rate changes, the black hole hasn't changed in distance, it hasn't changed in inclination, it hasn't changed in mass. The only thing that's changed is the mass accretion rate going on to the black hole. So the luminosity should change, but the area of that last stable circular orbit is set by Einstein's gravity, and that does not change. And so these simple ideas about what should happen in an accretion disk tell us that the disk luminosity should go as that peak temperature to the fourth power. Well, does it? So we can look. And what you can do is you can take X-ray spectra over the course of months and watch the mass accretion rate change through the inner accretion disk. You can watch the luminosity of the disk change. You can watch that peak temperature change. And then what you do for each one of these spectra, you can measure this peak temperature, you can measure the luminosity. You've got two numbers, you plot one against the other. This is luminosity, this is temperature, and the data are the red and the black points, where the cyan points show you the sort of systematic uncertainties we have on these system parameters like mass and distance. And that line shows you what happens if the luminosity went as the fourth power of temperature. I can turn it around, and I can do it instead in terms of a size scale. And you can see that that size scale remains constant. Despite the luminosity changing by over an order of magnitude, there's a radius, there's a size scale picked out by the data that remains constant. And this is quite amazing. I remember being amazed the first time I saw it. And I was amazed for several reasons. The first reason being, these ideas, I can sketch them. Surely black hole accretion flows are much more complicated than this. And I had read some quite influential papers that said, oh, accretion flows onto black holes, it's all going to be much more complicated than this. They'll be threaded by magnetic fields. Magnetic pressure means you don't have a last stable circular orbit that remains fixed anymore. And the emission, it's not really going to thermalize. It's all going to be much more complicated. And so I wasn't even looking at the data because I knew from theory that it was much more complicated. And it wasn't until I went to a conference in Japan and was talking to some of my Japanese colleagues, in particular, this one called Aya Kubota, and she said, the data show that the luminosity goes as the fourth power of temperature. And so I explained to Aya that actually black hole accretion, it was much more complicated than that. That there couldn't be such a thing as a last stable circular orbit just from gravity. When you had magnetic field pressure, there wouldn't be a constant. And she looked at me and she said, that the data show that the luminosity goes as the fourth power of temperature. So I said, and even if you had a last stable circular orbit, the emission need not thermalize. It can all be much more complicated. You won't have a stable spectrum. Aya looks at me and goes, the data show that the luminosity goes as the fourth power of temperature. So I try again from the beginning, saying, but you... And I got halfway through my first sentence, and I turned and I looked at the plot, and I said, the data show. And Aya is Japanese, so she did not go. She said, yes, the data show. The data show. And I looked at some of these data, and I realized it wasn't just that she had picked the best one to show me, though, of course, we always pick the best ones to show. Here are 6. All of them do the same thing. The data show that if you have spectra that are dominated by this disk component, then its luminosity and temperature change together in such a way that they're picking out a stable inner radius of the accretion flow. And that inner radius of the accretion flow is, while we don't know it exactly because we don't know some of these system parameters to really high precision, that stable radius is consistent with Einstein's last stable circular orbit. It is not consistent with the photon orbit. It's not consistent with the size scale of the event horizon. It is consistent with Einstein's idea of the last stable circular orbit in strong gravity. And there's something else you can pull out of these data as well. This is clearly that hot, X-ray hot accretion disk spectrum. There's a little bit of an X-ray tail. This is probably some particles accelerated to high energy by magnetic fields, because there are some magnetic fields in there. But where did all of this material go? Because remember, this is at the last stable circular orbit. This isn't even at the event horizon. We're not really seeing the rest of it. What happened to the rest of it? And this is why it's really interesting to compare the properties of black holes, which are the most extreme gravity we can possibly go for, with neutron stars. And the size scale of a neutron star is roughly the same as the size scale of that last stable circular orbit. And so you'd expect that their accretion disks see pretty much the same kind of gravity, the same amount of gravitational power as they come in. So their accretion disks see the same thing, but then the neutron stars, they have a solid surface. And so all that kinetic energy kept in that last stable circular orbit, as that material comes onto a neutron star, it smacks onto the surface, and all that kinetic energy comes back as a shocked hot plasma. It's coming from even smaller radii. It's got even more power than the hottest bit of the accretion disk. And so here was our accretion disk spectra from the things we think of as black holes. And here is what we see from things we know are neutron stars. They're very different. Very different. In the neutron stars, we've got something like a similar disk, but then we've got as much energy again coming out in this shock. Where'd it go in the black holes? Well, the thing about a black hole is it's got an event horizon, and an event horizon is a one-way trip to nowhere. And this material in a black hole slides below the event horizon and is lost, and its energy is lost from the universe forever. And so what you're seeing here is evidence not just for the last stable circular orbit in Einstein's gravity, but you're seeing also evidence for an event horizon itself, for the accretion flow sliding invisibly down in the black holes, whereas in the neutron stars, they shock, smack, and we see that energy come back. So I hope I've given you a picture as to why you might want to play with satellites, why you might want to go above the Earth's atmosphere, and also why you might want to hang out with the Japanese, because they tell you the data shows and make you look at data, which for a theoretician is a bit of a stretch. So I hung out with the Japanese quite a lot, and they flew a really innovative sequence of X-ray satellites, and the data from those satellites has really informed our understanding of how material falls onto a black hole. And in particular, I was involved in the latest Japanese satellite. In fact, one of my proudest accolades was that I was a Japanese member of the science team of this satellite. I don't know how Japanese I look to you, but I was a Japanese member of the science team. And space, of course, is risky. And there's always that moment where you take your beautiful, incredibly delicate instrument and you put it on top of a rocket and you light the blue touch paper and you stand very well back. And then you pace up and down in the kitchen and live stream it. And you can start to see the flames and you pace some more because this is quite a lot of years' work, thinking, planning, and it's a space mission and it's always really risky. And yeah, I was pacing the kitchen. You were expecting it to blow up because I had highlighted to you that space is risky, but no, the launch was perfect. The instrument checkout, we started to get data back from this new satellite. It was amazing. It was breakthrough new data with these sensitive new instruments. I had planned a year's sabbatical in Japan. We had our cases packed. We were an hour before going to the airport, and I got an email saying they'd lost contact with the satellite. Now that's not good news, but it's not necessarily disaster. These things do happen. You can switch your radio back on. But then when we changed planes in Charles de Gaulle, I got an email saying the orbit had changed. If your momentum has changed by that much, you are in trouble. And some days later, this little video appeared on the web. That's our satellite, and you can see it's kind of flashing. It's bright there, and faint there, and brighter there, and fainter there, and it was kind of spinning. Yeah, that's not good news. That is really not good news. Space is risky. it can all go horribly wrong. The launch is not the only point of failure, though it is an obvious single point failure. There are many other things that can go wrong as well, and there is always human error and software errors, and it was a series of unfortunate events. So I landed in Japan, and the new data from this new satellite that I had planned to work on, we were all, oh, okay. But it was around about that time that the film The Martian came out. And wave at me if you've seen The Martian. Wave at me if you've seen The Martian. Good, okay. There's this great line at the end where the hero goes, "It's space. It's filled with chance, circumstance, and bad luck. It does not cooperate. At some point, I promise, at some point, every single thing is going to go south on you. And then you have a choice. You can accept it, or you can get to work." So that's what I did. For my year in Japan, I got to work on other stuff and other projects, but also I lived in Tokyo for a year, and it had a host of unusual opportunities. Like, at one point, I got asked to come and do a talk in the British Embassy in Tokyo. And I was, as you can see in this picture, I was in the British Embassy in Tokyo, and talking about black holes to the ambassador, call me Tim. It was a surreal experience. You walk into this room, and there's a picture of the Queen on the wall. I texted my family, and they go, "Yes, Chris, it's the British Embassy. What did you expect?" Other unusual opportunities. BBC Radio 4 contacted me on email and said, "Would you like to do a talk on science and faith on BBC Radio 4? And I said, "Yeah, but I'm in Tokyo." And they said, "Well, that's fine. We can hire you a recording studio in Tokyo." And so here I am in a recording studio with a great recording desk in Roppongi, which is one of these really snazzy districts in Tokyo. I was just blown away that these things came out of what should have been a disaster year. So let's wrap it up, because I'm standing between you and a glass of wine. Black holes are the ultimate extrapolation of Einstein's gravity. But if you're going to look for an isolated black hole on the black background of space, really, that's really hard work. The accretion flow onto a black hole gives you a light source. M87, it's that light source that we use to see the black hole shadow. But honestly, that light source is so dim there, that accretion flow is so diffuse, it's very, very dim, and that makes their achievement doubly heroic. I'm not that much of a hero. I go for the easiest stuff. I go for the higher mass accretion rates, where you can have very, very bright accretion flows. And with X-ray astronomy, when you play with satellites, you can actually get evidence then for this key Einstein strong gravity idea of last stable circular orbit. You can get evidence for an event horizon. And you can start to explore Einstein's gravity in this strong field limit. And even when everything does go south, there are still some amazing opportunities, and it's really worth the risk. Thank you.
Thank you very much, Chris. So, open for a few questions. Yes.
Thank you. With the black hole binaries, given that the black holes probably formed from a supernova, how does the companion star survive that? I mean, I'm not a professional astrophysicist, but supernovae are very violent.
Yes. Very, very good question. It's worse, actually, for the neutron stars, because for the black hole, what happens is you get the supernova exploding, but the rest of the atmosphere is falling back down onto the black hole. And so, yes, you lose some mass in the supernova, but you swallow some of it down the black hole when you're making the black hole. For a neutron star, that's not the case. The neutron star, you have to not go over 1.4 solar masses. So most of your mass you lose. And it's only the very small fraction of binary systems where the kick that gives to the neutron star orbit happen to kick it towards the star that means that it doesn't unbind.
Okay, thank you. Another question, Hector, back.
First, thank you, and then a stupid question.
There are no stupid questions.
I've always wondered why people don't have the escape system equivalent for high, delicate, and expensive tech that they do for thick, cheap, and rather wobbly bits of biology with human beings are. You would think, considering how many there are of us and how cheap and expendable politicians think we are, that if we have escape systems, when we're shoved into space, then really expensive kit would have the same. Is there a reason for this?
Weight. Weight is the reason that to build escape systems for your instrument, actually, that would so increase the weight of the satellite, and you're always fighting against weight on a launcher. But it's actually not as bad as it sounds, because when you're developing one of these new state-of-the-art instruments, you've got it's called a flight spare. It's the one you use in all the vibration testing. I'm going to shake it and see if it falls apart. I don't really want to do that on my real one. I'll do it on my spare. And so they've got, in general, there is a flight spare. And in fact, we are now flying the flight spare in 2 years' time on another rocket. We're going to do this again. And I'm now a European member of the science team.
But can I suggest having a system whereby you could have a go at igniting the top stage, and then all you would need, all being well, would be a parachute system?
We'll suggest it to them.
Another question. Yeah, here.
The Einstein's...
No, you have to wait for the microphone to arrive, please.
Thank you. The Einstein think the Newton's gravity is not right. That's right. I agree with it. The gravity is not existed. But the Einstein want to uniform the film, but he go to wrong direction. The Einstein's the gravity have more problem than Newton's gravity, because Newton's gravity definitely not existed. But Einstein's gravity more wrong. Think about the solar system. Is the solar system?
Is there a question here?
Yes, I ask the solar system. From the courage, the closer one, more down, right? This solar system only 16 degrees, right? The 16 degrees is a
Could you come
a planet.
to a question that the speaker can answer, please?
It's not. This is the Earth is 23 degrees. To the.
I think I see what you're asking, yes. So I talked at the very beginning about how we use two-dimensional pictures, but really it's a 3- or 4-dimensional warping that we're talking about. But actually, you're right that Einstein has worse problems than Newton. Yes. But that's when we go to quantizing gravity, when we try and unify gravity with all the other fields, then we're in real trouble, because all the other forces we describe through quantum mechanics, and gravity doesn't quantize. And so we have 3 forces that work together, we understand how to unify them, and then we have gravity. And we can't make them talk to each other, and yet we know we need them both when we start to talk about things like the singularity, where we have really, really strong gravity on really, really small scales. Or the Big Bang, origin of the universe. We have really, really strong gravity on really, really small scales. And until we have a better theory than Einstein's gravity, we're not going to be able to actually explore what's the structure of that singularity. And until we have that new theory, we could maybe look in the data, but I'm just showing you these are the strongest gravitational fields we could ever hope to observe, and they look like Einstein says they should. So it's going to be really tricky to find observational ways to find this new theory of gravity that we all know that we need. We all know we need a theory of gravity that works with the other forces, and we don't yet have a good way of getting there.
Okay, let's thank our speaker again.